And start with the discussion of the mole, which is a really useful unit that we use to interconvert between things that we can measure, like masses and volumes, to things that we cannot actually measure, which is the number of particles. The first thing is you just think about things that are really, really small that we deal with in everyday life. So things like bags of rice, for example, or coffee beans, or if you want to buy nails or, paper clips and things like that. When we buy those things, we don't typically have to count them out in order to buy a certain number of them. So for example, when say we want to buy 1,000 coffee beans and count them out, but typically what we do is we just weigh them. And a certain mass of the coffee beans would then correspond to a certain number of coffee beans in it. Another thing that we do often is we tend to group these items into a specific unit that is corresponding to a certain number of these items. So for example, like if we buy eggs, we buy a dozen eggs. We don't just buy one egg. So a dozen is a group. A dozen of something is always 12 of that thing. So that's what we call a group unit. So the mole is also a group unit for particles. So what are particles? Well, particles are chemical entities. So they could be atoms, they could be ions, they could be molecules or formula units if we're dealing with ionic compounds, but they're basically things that are really, really tiny and we can't really see them. So we generally just use the word particle to represent these things. So a mole is a specific number of particles. A mole is just 6.02 times 10 to the 23rd particles. So it's a really large number, obviously, compared to say like a dozen, where that's just 12. How do we come up with this number? How did we say that a mole is equal to that many particles? We go back to our definition of atomic mass, which was something that we found by measuring all the different masses of isotopes and their percent abundance, and that number shows up in the periodic table underneath the symbol of the element, and it has a unit of AMU. So that mass is the mass of just one atom of a particular element. So in this case, this corresponds to silicon. So this is just the mass of one atom of silicon. Now, what happens is when we try to define the mole, we want the mass of 1 mole of silicon atoms to exactly have that same value of mass. So in other words, we want the mass of 1 mole of silicon atoms to also have the mass of 28.0855. However, the unit, of course, cannot be AMU because AMU is just the mass of one atom of silicon. So the mass unit here, if we're talking about a mole, is going to be grams. So it will be 28.0855 grams. So that's the mass of 1 mole of silicon atoms. Now the question is, how can we convert the mass of one atom to the mass of 1 mole of atom? And the conversion number that you need, such that the two numbers are exactly the same with each other, is 6.02 times 10 to the 23rd. Okay, so if this concept is not clear to you, let me walk through that with you right here. So AMU, remember, is equal to approximately the mass of a proton. So 1 AMU is about this number, 1.66054 times 10 to the minus 24 grams. We want the mass of the 1 mole of a particular atom to have exactly the same number value with a different unit. So let's take a look at carbon, for example. Well, what's the mass of just one carbon atom? If you look it up in the periodic table, it's about 12, right? It's 12.01 AMU. That's for one carbon atom. Now, what about 1 mole of carbon atoms? Well, we know that 1 mole has this many carbon atoms, so we would multiply 6.02 times 10 to the 23rd carbon atoms times 12 AMU, which is the mass of one carbon atom. So 12 AMU per one carbon atom. Now, once we do that, we get the mass of 1 mole of carbon atoms, but in units of AMU. That's not really useful for us because our scales don't read in AMU units, but they read in grams units. So what we need to do is then do one more conversion, which is just the conversion between AMU and grams. And we know that AMU is equal to this many grams. So we do that conversion right here, multiply the result of this calculation with that number. Look at what we get. We get 12 grams, which is the same number as the mass of one carbon atom, except that the unit here is grams, the unit for one carbon atom is AMU. So this is really to emphasize that if you want to know the mass of 1 mole of any element that you have in the periodic table, all you need to do is use that same exact number that we already have in the periodic table. The only thing is you have to change the unit. You can't say the mass of 1 mole of sulfur is 32 AMU. You have to say the mass of 1 mole of sulfur is 32 grams. Now the mass of one atom of sulfur is 32 AMU. That number, when we use it in the unit of AMU, we call it atomic mass. Typically when we use it for the mass of 1 mole of that same atom, we would call it the molar mass. Molar mass here means just the mass of 1 mole of something. Now what about if you have compounds or molecules? Well, just the same way as when we try to calculate formula mass or molecular mass, we have to add all the different atomic masses together. The same idea here. If we want to know the molar mass of glucose, which has this formula C6H12O6, all we need to do is add the molar mass of 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, giving us a total of 180.16. The unit here is going to be grams, again, as I said. Now it's grams per 1 mole, so a lot of times we would just write it as grams per mole. There's this path here that you can think about in terms of converting from mass to number of particles. So what we just have, this molar mass, is a conversion factor that would take us from the mass of an element that we measure in the lab, for example, on a scale. We can take that mass and then convert it to the number moles. Because the molar mass has units of grams per mole, well, that means it can convert between grams and mole. And then once you have it in moles, you can then use that conversion 6.02 times 10 to the 23rd, which is called Avogadro's number, to convert that number of moles to number of particles. And again, particles could be atoms, could be molecules, could be formula units, could be ions, whatever you want. If you're doing this for compounds, it's really the same thing, except that you have to calculate the molar mass of the compound itself. But once you have that, you can use it to convert between the mass to number of moles of the compound, and then you can still use Avogadro's number to convert from number of moles to the number of particles. Now, let me do one example. Sugar contains approximately that many sucrose molecules, which has a formula C12H22O11. Question is, what's the mass in milligrams? So we were told that we have 1.8 times 10 to the 17 of the sucrose, which has this formula. And this is a molecule, right? Because it's a covalent compound. Remember, covalent compounds are made up of nonmetals only. They want you to get your mass. So how do we do that? First, we're going to convert molecule to mole. And that, you just need your Avogadro's number. Now, once you do that, you still need to take your mole to your mass, grams and moles. And that goes through the molar mass. So you got to go to the periodic table, find out what the molar mass of carbon, hydrogen, and oxygen, and multiply them by 12, 22, and 11 respectively. So you're going to take 12 times 12 grams per mole. I get this from the periodic table. And then 22 times 1 grams per mole. So hydrogen is 1. I'll just show you real quickly here. Right here, hydrogen 1.00794. And then the last one is oxygen. That's about 16 plus 11 times 16 grams per mole. When you calculate all that, you should get 342.3 grams per mole. So that's the number I'm going to go up here on the top in my calculation. They're asking me my mass in milligrams. So I need one more conversion, which is just a conversion between grams to milligram, 1 and 10 to minus 3. So when I plug in all of those numbers here in my calculator, first off, this cancels, and then the mole cancels, and then the gram cancels as well. So my final unit is milligrams. I get 0.102 milligrams. The only thing that's unique about molecules or bigger compounds is that they're composed of many atoms, right? So for example, 1 mole of glucose, C6H12O6, contains 6 carbon atoms. So that's the way we would say it. We can say that 1 molecule of glucose has 6 carbon atoms, or we can say 1 mole of glucose has 6 moles of carbon atoms. So that 6 here is a mole-to-mole relationship between glucose and carbon atoms. So if I know I have, let's say, 2 moles of glucose, that means I'm going to have 12 moles of carbon atoms because the relationship between glucose and carbon is 1 to 6. So let's try number B right here, okay, which is how many oxygen are in 3.5 grams of KClO4. Start with our KClO4, right? Potassium perchlorate. We need to convert that to number of moles because the formula is a relationship of number of moles. So we always have to convert back to moles. We're going to first have to multiply this with our molar mass, right? Molar mass is 138.55 grams per mole. Again, you can do this through the periodic table. So just to be clear here, this is KClO4, which is the compound. And so that's how that cancels. Now I'm going to have to multiply this with something that would cancel out my mole of KClO4 and take me to oxygen. So it's going to be a relationship between oxygen and KClO4. Well, given the formula, there is 4 oxygen for every 1 KClO4. And so that's going to cancel out with this one right here. Okay, so now that I have the number of moles of oxygen, the last step I need is to take that and convert it to the actual atoms of oxygen. I would need to take moles to atoms of oxygen. Well, this is just given by Avogadro's number. So 6.03 atoms to 1 mole. That's going to cancel that out. With correct sig fig, this should give you 6.1 times 10 to the 22 oxygen atoms. Okay,